This YouTube is the second YouTube video for Chapter 6, which is a chapter all about arrays. In this video, we're going to talk about arrays and functions, and here is my array of happy faces, because you all are so happy. Okay, so before I talk about using arrays and functions, I want to point out some of the properties of arrays that are different from the other variables that we have been using in the past. So this I will illustrate and explain it by use of an example. So here I've declared an array called array with 5 elements, character elements in it. So I've put 5 T's in an array. And then line 9, if I print out what array is using a string conversion specifier, and there's array, it'll definitely print out 5 T's all on one line because I didn't print it out with a for loop. So okay, so if I print the string using a string specifier and I print array, that's what I'll get. Line 10 is where it gets interesting. Now I print, but I have this ampersand symbol in here, which is indicates that I'm pointing to an address of array. So and then I'm using a %p, which is a conversion specifier for printing addresses. So this line of code says print me the address of array element 0, and when I do that I get an address, an address in memory in the computer. It's a hexadecimal number. Yours may differ depending on how much memory you have on your computer, but this is a hex address in memory, and what's stored at that address is a T. It's actually not a T, but what the ASCII value is for T. So something in hex is stored in this memory location. In a different video, I'm going to show you a debugger that lets you look at what's in memory, and I'll show this to you explicitly. So at this memory location in your computer, the value that will be stored there is T, but it's an ASCII T, so you can convert that to some number if you do the ASCII lookup table. Line 11 of the code says, show me the address of array. Not array element 0, but show me the address of array, and I get the same address. That's because the address of array is the address of the first element in the array, and everything in array is contiguous in the memory. And then line 12 says, just to make it interesting, print me the address of array element 1, and sure enough the address incremented by 1. So if I were to look at memory, these are contiguous locations in memory, and there are 5 locations of memory, and a T is being stored there. So that's the first thing I want to point out, that when I refer to an array, I'm referring really to the address of the array. So now let's talk about using an array in a function. I have a function that says find max, and the parameters that are required of this function in the function definition is it's expecting an integer array, and it's expecting an integer. So recall that a function, the format of a function definition, you have to have its return type, its function name, and the thing in the parentheses are the parameters. So your parameter can be a double, it can be a character, it can be an int, it can be a bool, which would be like true false, and it can be an array, an array of integers in this example. Previously, when we had a function and your main calling program called the function, the actual value that you put in the parentheses when you called the function was passed into the function, and the function did its thing, its calculation or whatever it had to do. But that actual, in this case, like an integer, is actually passed into the function. The actual value of the integer is passed into the function, and the function does its thing. The function could not go back to the main program and modify the value of a variable that was in memory unless you set it up to do that. That was not the default. Your variable would be out of scope. So when I have an integer or double or any of those data types that we've already talked about. And I do a function call. The value that we pass into the function is the actual value, and this is called a call by reference, a function call that's a call by reference. With an array, it's different. With an array, the thing that gets passed into the function is the address of the array, and then the array can go and do its thing to the function can go and do its thing to the array, but the function can actually modify the contents of the array, which is different than what we're used to with the scope of our variables before. If I were to actually do my function call using this function that I have defined here, it might be something like what I've handwritten down below. I've declared an array called A with 5 integers in it, and then I'm just going to print the maximum of the array by doing a function call to find max. So notice how I make my function call. I pass in the name of the array right here. There's no square brackets, and then it's expecting an integer, so I passed in my integer right here, but that's the name of the array. So I pass in the name of the array, but what's actually being passed into the function is the address of the array. So your book has an example to illustrate this. A little bit hard to follow maybe, but it's a nice example for illustrating it. It's this example 613 on page 233. Right? Yes, it is. So let's look at a little bit what we have going on. Here's a function prototype for a function that's going to modify an array. It takes the parameters are an array and the size of the array. I see your author has again used size t. It's okay with me if you just call it an int size. That's fine. Notice this size is in lowercase letters, so this is a parameter, whereas this size in the definition is a constant to be used by the program. So my next function prototype is a function that's going to modify just one element in the array. So E is going to be some element in the array that will be passed into this function call. Let's go look at the functions themselves before we go look at main. This is the modify array function. It's expecting an array, and it's expecting an integer, which is the size of the array. And what it goes and does is it multiplies each element of the array by 2. So the really interesting thing about this function is that it multiplies each element of the array by 2, and it's actually modifying the array in memory. So when I go back to main, my array has been modified. The second function here is modifying an element, and I'm going to expect to pass an element into this function when I call the function. I'm actually going to call the function with a element 3, and it's going to multiply that element by 2 and output the results. This one will not modify the original array that exists outside the function that exists in main, because this is like an ordinary function where we do a function call, and the actual value is what is passed into the function. It's actually a copy of the actual value from main is passed into this function, and the function will do its thing. So let's look at what the main function does. So I declare A using this constant size, right? I declare A, give some information to the user. Next part here, I output the original array to the standard output so you can see what it looks like. Next, I do a function call to modify array. So this will pass the address of the array to the function, and the function is going to multiply everything times 2, but the interesting thing is it's going to change the whole array. So now my next piece of code to here, I'm outputting the array once again, and you will see when I run this program, you will see that the array has been modified. Everything's been multiplied by 2. Now I'm doing a function call to modify just an element. So function call to modify element, and I pass a element 3 into the function. So the actually a copy of the actual value of A element 3 is passed into the function, and the function does its thing. And then once again, I'm going to print out the value of A element 3 now. So I did this function call to modify A element 3, and I'm going to print what the value is of it now from what it is in the array. And you will see that it didn't change the array at all. I was able to use the single element like I did like ordinary functions, an ordinary scope of an ordinary variable, but the array did not get changed. So I compiled this program and ran this program. Here it is. So there was the original array right here. Here's after I called the modify array function, so everything is multiplied by 2. Then I passed A element 3 into the modify element program. So A element 3 is that's the 0th element, the first, second, third right there is a 6. So that's A element 3. I multiply it times 2 after I call modify element. So the value of A element 3 is now 12, showing right there. But back in the main program, I say, well, what is the value of A element 3? It's 6. It did not get modified by this function that only worked on a single element. If I work on the entire array, I modify the array. If I work on a single element, then it's like an ordinary function. I should say also, if I have a function that is expecting an array as a parameter, I can modify a single element in that array. But the key is that the function was expecting an array address to be passed into it. There are occasions when you don't want a function to be able to modify a array. And just to illustrate, I'm going to modify this program just a bit. So this modify array, I'm going to, this is the function definition. I'm going to say it's a constant. So this says that my array is a constant and can't be modified. So let's see what happens when I compile. Okay, I'm going to get an error. So I have conflicting types here. Anyway, it doesn't like that I've declared it as a constant because now I'm trying to change it and I'm not allowed to. So you will get a compiler error if you do that. So be careful if you actually want a constant to be declared. Don't try to modify it in a function. So arrays have a lot of data in them, and one of the very common uses of arrays is to search them for a particular piece of data that you need out of the array. Very common application. So now we're going to talk about searching arrays. I'm going to do 2 examples of typical algorithms. There are others, but at an entry-level programming class such as this, these are the 2 that always get presented to you no matter what the language is. So one's called a linear search. This is the brute force method. It's inefficient. You just literally go through the array element by element until you have a match, and then you can return the position of the match where it is in the array. So that's the brute force or linear search method. And then there's the clever binary search method, which we'll go over. It's like a 3-page program in your book, so we're going to go over it. Your book neglected a very important component of this algorithm, so I will talk to you about it. So first let's talk about the linear search. So linear search, you literally just go through the array element by element and find the match. The thing that you're looking for in your book is called the key, or the user input, or the value that you're looking for in the array. So I have the textbooks, not quite the textbooks program. I have the textbooks program here, which I've modified a little bit because there's certain things that I like that make it more readable to me. Whether or not you agree to me, you can agree with me, that's your opinion, but you can follow along with what I did and see the minor changes that I did, and you can see what's happening in the book too. So the first thing I did change in my program is I don't like using size t. I especially don't like declaring this parameter over here in the function prototype. I don't like saying size t and then calling it size. So size t space size, just forgive my simple mind, but that just confuses me. So I changed all my size t's to ints. Let me show you how you do that, just for the fun of it, in case you want to do it too. So when I double click on the int, all of the ints in the program are highlighted. And then if I go up, let me move down. If I go in the search right here, there is a, let me get this to where you can see it. Search. There is a replace option in this pull down menu, and if I replace, I can say replace all the ints with something else, and that's what I did. I replaced all the size t's with ints, and I replaced them one by one because you had to be careful. int is embedded in the word print, so be careful there, because I first did it and messed up. But anyway, so that's how I changed all my size t's to ints, just because to me it's a more readable program. But that's just me. Maybe you like size t's. So far I haven't seen any advantage of using size t, and as a matter of fact, when I use size t, I have to put that extra option when I compile so that it's recognized, the dash standard equals C99. Okay, so that was the first thing I did. The next thing I did, I'm walking through this function. This is my function prototype that declares the linear search function, and you can see that it's getting its parameters are a constant array that cannot be modified. So here's our use of constant right here. Int key, this is the value that you're looking for, and then the size of the array. Almost always when you make a function that's using an array, you're going to have to be worried about what the size of the array is. I think I'll look at the main function first. So I'm going to create an array, just some data. It's actually 100, an array of size 100 of ints, and it's 0, 2, 4, 6, 8, 10, 12, etc. And I wanted to look at the array, and I wanted to see the indices that are associated with each element of the array. So I added to the program this print statement so I could look at the data, because at some point I get asked, when I execute this program, it asks me for what number I want to look for, what the key is, and I wanted to look at the data and make sure the number I asked for was in the data. So I just printed out the data here for my benefit. So tells the user enter the search key. Remember, that's the value you want to locate. So I do a scanf and store it in a location called search key. And what I want to know is where in the array this piece of data is located. So I want the index to come back to me, the position in the array. So this is the answer that I'm looking for. So I call the linear search function. It finds the key in the array. It returns the index of the key, the value that we're looking for. And then here's just displaying the results. If I entered a value that was not found in the array, I have accounted for that by saying if the index is not equal to -1, then find the value, return the index. Else, I'm going to put that the value is not found. So now I'm going to look at the actual linear search function. Here's the function definition. It accepts a constant array of data that you cannot change. It accepts the value that you are looking for. It's looking for having the size of the array. So I loop through and I basically just say, I go through each array element. If the array element matches the key, I will return its position in the array. If not, if there was no match, I'm going to return -1. So that's part that the main program uses. If you got a -1 returned, then you'll say the key, the data piece that you were looking for was not found. So I ran this program. I compiled it and ran it. I already did it, so the results are already here. So what I did was show the data, what its position was in the array. For example, index in position 0, with indices 0, the data is 0, and index position 2, the data is a 4. So now I can see actually what the data is. That was just for my own understanding. It says enter a search key. I wanted to find 188, and 188 is in position 94 with the indice of 94. So that's how the program works. If your array or your set of data is very large, this is an extremely inefficient method of searching for your answer. So a much more efficient method is called the binary search algorithm. So it is a very clever algorithm that is much more efficient than the sequential search. Oh, the linear search is also called sequential search in other textbooks. So the example, your textbook example does a binary search algorithm, but it doesn't explain very well, unless you spend some time in the program, what the algorithm does. So I have an illustration for you to explain the algorithm before we actually look at it. So this is my illustration. But rule number 1, I must emphasize that the array must be sorted into ascending order. If you do not sort this array into ascending order, this algorithm will fail you and you will not find the value you are looking for. Binary search, by the way, is such a useful algorithm that in other programming language, C# for example, binary search exists already as a function for you, so you don't have to develop the binary search. But binary search is an algorithm that just about all C programming languages, and even when I teach C#, we always go through how to do binary search. So here's the algorithm. First, let's assume I have this piece of data, right? This is my array that I want to search, and I want to find the number 12. Rule number 1, sort it into ascending order. So I have already sorted it into ascending order, which is lowest to highest. So I want to find the 12. The way you do it is you start in the middle. So my algorithm has to find the middle indices, right? You start in the middle, and so there are 1, 2, 3, 4, 5, 6, 7. Odd is a nice amount. So I start in the middle. The middle is a 7. The middle of the array is a 7. So 7 is less than 12. So 12 must be at least in the last half of the array. So half the array I no longer have to search. I've already thrown that part out. So I repeat the process. Go to the middle of the next section. And is it a 12? Yes, the middle of the next section right here is a 12, so yes, the search is finished. If not, if our number is not there, then you continue the search either in the upper or lower half of the array. So I was lucky here. This was an odd array. The other thing you have to be careful of is duplicated numbers. So there are some subtleties with doing the binary search. But now let's look at the example that your textbook has. And then I'm also going to show you an algorithm that sorts into ascending order. I think you have seen it a little bit in my programming lab. I think they called it the swap. I think they called it a swap function. But I'm going to go back and revisit it because, as I said, binary search will not work unless your data is sorted into ascending order. This is problem 619 in your textbook, which is their example of binary search of a sorted array. What they mean is one that's already been sorted into ascending order. So keep in mind this does not work if your array is not in ascending order. I bet I give you a homework problem where you have to put it in ascending order. Okay. So I'm going to look first at the actual binary search because the rest of the program is fluff, just making the program usable for you. So this is the binary search function definition right here. it takes an array that's already in ascending order. Your array is being kept constant, which we expect at this point. The search key is the thing that you're looking for, and this low and high, by the way, I changed all my size t's to ints because it's more readable to me. Low is the low index. When you first start off, that's a 0, and high is the high index of the array, which will be the last value, the size of the array minus 1, actually. Because just think about it, if your array size is 10, then the highest indice is a 9. Okay, so this is what we do. We're going to do this loop, this while loop, while the low index is greater than the loop until the low index is greater than the high index. So this is what we do. You enter the function and you say determine the middle of the subarray being searched. So the first time you pass through the array, you're searching the whole array, and the middle is the low plus high divided by 2. Got a little problem here. Make sure you, well, maybe it's not a problem, because low plus high divided by 2 is going to round up if you have an even number in the array. So just nice thing for the user to display the array being used in this particular, subarray being used in this particular loop iteration. So it will go ahead and display it. This is the indice. Oh, this is the row of the matrix, and it'll show the low, the middle, you define the middle, and the high. So, and then if the key matches this middle term, you return the middle. Else if, you got to continue searching. If the search key was less than the middle, then you're going to search the low end of the array. Else if the middle is the value of the middle is higher than the search key, then you're going to search the upper half of the array. And if you don't find the search key, you'll return the -1. So that is the meat of this program, the binary search function or algorithm that's actually determining when you get a match by subdividing the array into half sections at a time. Notice also that while you're in this particular function, this function called binary search, this function calls another function. This is the print row function. So note, a function can call another function, and it makes it program more readable. Otherwise, this binary search part would be rather long. So this emphasizes the binary search itself, and when I want to display some information, I call the print row function. So now there's another function called print row. Where is print row? Print row. Here's the print row function. It prints one row of the output, then it shows the current part of the array that's being processed. So that's what this function will do. And it's taking values passed to it from the function that called this function, which is kind of cool. Print header, that's just header for each time. Oh, this print row, else if print, okay. Print header is a function also, which must occur in the main. Yeah, occurs in main. Okay, so here we create the data. We're in main now. Create my data. Again, it's just counting by 2s. Get the key from the user. Print a header, which I call the print header function. Doesn't have anything returned. It just does its thing. And then get the position of the value that we're looking for, get the position of the key. So just sort of similar to the other program, the binary search is going to return, actually this one returns the key, not the position of the key. Let's check that. Yes. Okay. So let's run the program. Magically already compiled and ran it. It says enter a number between 0 and 28. I entered 5, which I already knew that data was counting by 2s, so 5 isn't going to be there. So first pass through the binary search algorithm. It's going to search through the whole array. There's the whole array right there. These are the indices or the subscripts of what's in what position. There are 15 elements in this array. So the middle is number 7, so it puts a star there. The nice user interface print row. What was it called? Print row, I think it was. We'll put a star there saying that that's the middle. 14 is not 5. I'm looking for 5. 5 is less than 14, so I'm going to search the lower half of the array now. I find the middle. The middle is number 6. 6 is greater than 5. So again, I'm going to search the lower half of the array. The middle is 2. 2 is less than 5, so I'm going to search the upper half, which is 4. That's the end. I didn't find 5, so I say 5 not found. So let's run it again. Let's enter a number like I'm looking for 24. So 24, first I find the middle. The middle is 14. 24 is greater than 14, so it must be in the upper half. So here's the upper half of the array. The middle of this upper half is a 22. 22 is less than 24, so again I search the upper half. Then I find 26. 26 is greater than 24, so now I search the lower half, and I found it. I found 24 at index number 12. So I'm going to modify this program and put, it should work just fine with an odd number in the array, but let's just double check it just to make sure. I'm going to make my size be, no, it was working with an odd number right now, which I said was the nice one to do. Let's see what happens if the program has an even number. I'm just curious, so I'm going to try it. Because what do you do when you have an even number? I think it rounds up, but let's see what happens. Enter a number between 0 and 28. I'm going to enter 15. So it still starts at 14. Still finds it okay. Let's try it one more time. So that's good. It just rounds up and takes the upper half. Shall I run it with? I'll run it with 12. Yeah, it works just fine. It's just an uneven split of the array. One more time. $13. Yep, we're good. It finds it. So I'm going to show you how to put your function, your array, into ascending order, because binary search does not work unless your array has been put into ascending order. So this is a little bit confusing. It does use a swap that you saw. I think you saw it somewhere in my programming lab. But not only do you have to do a swap, you're rearranging things in a whole array. Whoops. So this is the function definition here. It doesn't actually return anything. It's actually modifying the ordering of the array, and the array exists outside this function, but the function will modify the array, that place in memory. It takes an array as the parameter that is an array, and then this is number of points. It's how big the array is. So basically what you're going to do is go through the array and decide if one number is bigger than the other number, the next number in the sequence. If it is, you're going to swap their positions, and you have to slowly work through the array and reorder the array. So I'm going to use this sequence of numbers. No, I'm going to use a different sequence of numbers. easier than that. But I'm going to use a small array, and I'm just going to walk you through showing how this particular sorting algorithm, sort ascending, will work. So I'm going to use an array with the numbers 5, 7, 2, 8, 9, 1. So that's my array. There's 6 elements in the array, and they are not in ascending order. So this array gets passed into here, and now let's see what happens. So K, J, and M are indices that you're going to use during this process. They're iterators. And the thing of the hold is the place where you're going to hold the current value that goes into a particular position. So the I, J, and K are used for the swapping function as you go through the array. So let's just go one first pass through the loop. I'm going to start off with K equals 0, and K is less than the array size minus 2. And then as you go through, K is going to get incremented. So the first thing I do is say M equals K. But first time through the loop, K equals 0, right? K equals 0, M equals 0 as well. K equals 0, M equals 0. So that M is also equal to 0. And then J gets K plus 1, so J equals 1. Okay, fine. So far, so good. Then it says if X element J is less than X element M, we're going to swap M and J. So X element J is a 7. X element M, which is 0 right now, X and is a 5. So I say, is 5 less than 7? No, 5 is not. 5 is less than 7. My question is 5 less than 7? Yes. So this is in good order. This is in ascending order. These first two elements are in ascending order. So I'm not going to do a swap. So actually what I'm going to do is that M is now equal to J, so M is now equal to 1. And I'm going to do a hold. I'm going to hold X element 1, which is a 7. And X element, let's just pause here for a second. What's happening? So at the this is the swap function. We don't do a swap function. If X is, we only do it if 5 is less than 7, then we keep things the way they are. Let's say that again. J is 1. Yeah, so just thinking here, X sub J is 1. X is the matrix going through here. Remember, X is whatever the matrix is going through here. If 7 is less than 1, you're going to do something. But 7 is not less than 7 is not less than 5, so we don't have to do a swap. And we keep things the way they are. So that means K is still 0, right? K is still 0. X element 0 gets the whole value. So 5 stays in its current position. Correct. 5 stays in its current position. So now let's go to the next iteration through the loop. So I'm going to iterate now through the loop. K is now 1. So next iteration through the loop. This wasn't correct. Next iteration through the loop is K equals 1, which means J equals 2 by this line, by this for loop right here. And so we go through and we have a comparison between the 5 and the 2. And so the question becomes, is 5 less than 2? No. So we have to swap those positions. So now our array looks like 2, 7, 5, 8, 9, 1. That's what it looks like right now. So I'm going to go through the loop again. J now equals 3. And I will do a comparison. Is 2, I'm comparing 2, is 2 less than 8? Yes. No swap. Keep the position. Keep the order right now. Now J equals 4. When J equals 4, your questioning is 2 less than 9. So I'm testing to see if 2 is the lowest value in the sorting process. Is 2 less than 9? Yes, no swapping around. So the swap is always moving the lowest value to the first position. J equals 5. Is 2 less than 1? No! So I have to do a swap. And when I do a swap, now the ordering here is 1, 7, 5, 8, 9, 2. Now what happens here is you've gone through the whole array and you've found the lowest value and you've put it in position 1. So I'm no longer going to look at this part of the array. I'm going to look only at this remaining part of the array. So we start the process over again with k equals 1 and j equals 2. So we start right here, k equals 1 and j equals 2 with 7 and 5, and you repeat the process. Is 7 less than 5? No. Do a swap. So now our array is, and remember, 1 has stayed in its position. 1, 5, 7, 8, 9, 2. And I'll walk through, and eventually 2 is going to get moved into this position. And then k and j will start with k equals 2, j equals 3, and you'll walk back through the for loop again. So this part is the ordering, the test, do I have the lowest position? This part is the swap function, which I believe you saw in the My Programming Lab. We can also have 2D arrays, two-dimensional arrays, which you have rows and columns. So this is a row, this is a column, and you have to have 2 indices to associate with a position. So this is row 1, column 1, so position 0, 0. So we'll talk about the syntax of how you do that in a moment. How do you declare a 2D array? I have some examples here, characters and ints. So here's int. Here's an int called numbers. You have double brackets here, and then notice when I initialize it, I have row 1, row 2 here. I just resized a little bit. So this is row 1 of data, row 2 of data. Each row is in curly brackets, and then the entire array, 2D array, is also in curly brackets. You could also say a matrix. Here's a character array. Its size is 4 rows by 3 columns. Notice that I've put each character in its single quote and showed each element individually. Also notice that numbers are also characters. You cannot be they will treat it as a character in your program that uses it. Here's another character array called My Words. It's 10 by 10. I have the quick brown fox. This is row 1. I can have row 1, row 2, row 3, row 4. I do not have to fill up the whole 10 memory locations I've allotted for that string or that array of characters. So I'm going to use that example coming up next, how you would output the 2D array by using nested for loops. So I have my words array, which is the quick brown fox, and I have a nested for loop, which you're going to have to play with a little bit to see which way. Are you printing rows first or are you printing columns first? So it turns out that this outer for loop is the number of rows information, and this inner loop is the information of each row. So it's the column information. So there's 10, looking back, let's see how we went. Anyway, you can see how the result turns out. So this is row 1, this is row 2, this is row 3, this is row 4. So there are 4 rows, that's the outer loop, and then the inner loop is printing the information in each row. So this is the first 10 elements, because I have 10 columns permitted, because it's the column information. There's 10 here, there's 10 here, there's 10 here. So there's empty spaces here that are not showing. I'm going to just enrich this lecture a little bit with more about character functions from the C-type header file. I already introduced to you some functions that you get by including strings.h, but you can also include C-type.h excuse me, and get some other interesting functions that you can use. So when I store a string in an array, each character is going to a location in memory, but like this says, this is a string. See, can I make that a little bit bigger? I can. So each character gets a location in memory, and then it's translated to its ASCII code, like a capital T is an 84, a little h is a 104, and that's stored as a hexadecimal, actually binary value in your computer somewhere. But at the end of the string is this /0 character. So as I mentioned before, this special character shows up at the end of the string, and it's called a null character, and you write it as a /0. So a string is always terminated by that null character, so the length of the string is always greater than the number of characters in the string by 1. This is just a little piece of code that shows you, proves that to you, that there is this existence of a null character at the end. Although we can find the length of the string with the string length function, this is a little thing that's proving it to you. So I have a string to be or not to be, and I'm going to use a while loop, and I'm going to say while I'm starting with count equals string element 0 is not equal to the null character, I'm going to implement, and I'm going to print, go through this while loop until we hit the null character, and then after the null character occurs, I'm going to print out the count. If you run this little piece of code, it will prove to you that the length of the string is one count higher than the characters that and spaces that we see right here. Speaking of strings, you can also make reusable constant messages. Remember, we've introduced this concept of a constant, something that cannot be changed anymore. But if you declare a constant, it has to be with all capital letters, not because the compiler expects that, but because that's our style conventions. So I have a constant character message array right here, which is to be or not to be, and I can use it anywhere in my program, and I cannot change the message. Using the string.h functions, the ones that are given to you if you include string.h in your file, you can also compare two strings. This is a string compare. I showed you string length before. I showed you concatenate strings. You can compare two strings. So I have a string 1 right here that's the quick brown fox, and another string 2 that's quick brown fox, and I can do if, and the way string compare works, string compare string 1 and true is greater than 0, print that string 1 is greater than string 2. And you say, wait a minute, that's a string, it's text, how does that work? So the way it works is it looks at what the binary value in hex is that's stored in memory for each one of these characters. So a T, this must be in hex this time. Yeah, the other example I had was in decimal, but this is in hex. So a T is a hex 54, and that's equal. So if they're equal, but it's based on their numeric or ASCII value. So you can see if they are equal, you can see if one is greater than the other, but the result of calling this function is a true or a false. This is an example. I have two strings. One is string 4 and string 5, character strings. Actually, I shouldn't say they're strings. They're arrays of characters, which makes them a string. One string is I want to eat pizza, and the other one is I don't want to eat pizza. I do not want to eat pizza. And then I need result. So I do a string compare. If string 4, string 5, and I'm only comparing the first 5 characters. I don't have to compare them all. If it equals 0, then they're equal. So it'll return a 0. If it's equal, that's true, and it will return a 1. If it's not equal, that's a false, and it will return a 0. That's what it will do. And then this just lets me print whether they're equal or not equal. So if you do a test, if always returns a true or false, but false equates to an int 0 and true equates to an int 1. Our next chapter is about pointers, but I'm going to give you a sneak peek because we're talking about strings right now. So so it's a sneak peek of using string searching functions. We've been talking about searching, we've been talking about strings, but how do you search a string? Maybe I want to find something, a phrase within the string somewhere. So this is a sneak peek about pointers because we will be talking about pointers in the next chapter. So a pointer is a variable that stores the address. If you remember in our earlier YouTube that I showed you the address where the array exists. Well, I can also save what that address is. It was a hex value, and I can save that. So a pointer is a variable that stores the address. Doesn't store the data that's stored at that address, but it stores that address. And I have an example right here. This is the notation, by the way. I'm going to show you the notation. I have an int declared called number, and it equals 25. So you know that 25 is stored in memory somewhere, but it's stored at a certain address. In my little illustration down here, which comes from that C textbook, PDF textbook that I've placed in your resource folder, it says the value of 25 is stored somewhere in memory. It happens to be stored at the address 1000. This is a hypothetical number because it's probably 0x something 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 in hexadecimal. So the variable name is number. The variable, it's actually called an identifier. The identifier for that variable is number. The value is 25, and it's stored at address 100 in your computer. Another convention is that a pointer, the name of a pointer stores an address, right? Our convention is to put a P in front of the variable name so that it's identified as a pointer. So we were introduced to the ampersand before. That's an address. So if I declare this variable, it's with an asterisk in front of it, the P number, that's an address, and it gets the thing here, the address of number. So if I were to say what P number is, it's going to be an address. But that's also a variable. P number is a variable, but the value that it's holding is an address. So P number down here is a variable. The variable is at location 1004 in memory, and its value is 1000. So the asterisk here is called a dereference operator, and its effect is to access the data stored at the address specified by the pointer. More about that the next chapter, but I wanted to show you that it's also possible to search a string. If I were to search a string, keep in mind that each one of these characters, and a space is a character, is stored at a location in memory. I can actually return the address where a substring exists. So maybe not to be is what I'm searching for. I can return the address of where not to be exists. So that's what we're going to cover later on, but that's one of the main ways we search a string. One more thing I'm going to talk about this chapter is the variable size arrays. I think that's just about the last section in your book. I'm going to use some simpler examples than they did to try to make the point. And then there was one other thing, last thing I didn't talk about in this chapter is they had a section on using the word static. I am going to make a separate little video that talks about some of the things I'm seeing in your programs, which is the fact that some of you are giving variables higher privileges than they need to have. So I'm actually going to do a separate little YouTube on the privileges and the permissions that variables are given in a program, but that's a separate presentation. Some error that I'm seeing in people's programming, or just not good programming practices. They work, but you don't give your variables too high of privileges. So variable size arrays, that means that you don't always know the size of your data when you go into a program or you're executing a program. So you want to be able to account for the size of your data. This is especially true when we start doing reading in files of data and exporting files of data to a text file. So you want to be able, and there's several ways actually to get the size of things, but the example that their textbook uses the function called size of, and I'm just going to show that to you actually more by example. So I have a little piece of code right here that I wrote that just declares an array. It's an array of 0, 2, 4, 6, 8, just like we were doing in the example a moment ago. So I create the array, and then I want to know how big my array is, so I tried just using the size of function right here. So I'm going to I create array A, and I say the size of A is, and then I used my size of function. So this is an array of ints, so let me just show you what the result is. So I just executed the program and I got size of A is 64. So you think, what just happened here? Size of A is 64, but this is only an array of 16. The size of A is 16. So what happened is that size of function tells you how many bytes are being used. So this array of 16 is using 64 bytes of computer memory to store the value. If I wanted to know how many values are being stored, you need to know how many bytes it takes to store an int. Looks like it takes 4 bytes to store an int because 64 divided by 16 is 4, so it must be 4 bytes to store an int. But we can prove that by saying divided by size of int. And I can just leave it as an int right there. So if my size of an int is 4 bytes, then I'll have the size of A, which is 64 bytes, divided by 4 bytes, and it should give me the answer of 16. So yes, now the size of A is 16, and that's correct. So if I had declared all of this as a double, of course my answer would be different. Let's just see what size of A is as a double. Well, how much is a double? How many bytes does it take to store a double? Okay. Size of A is 128 bytes, so I have to divide it by size of a double to find out, again, that we'll get 16 as how many pieces of data are being stored in the array size. So if you have an array that you don't know, especially since if you've imported it from a file, which you haven't covered yet, if you have an array that you don't know what the size of it is, you can use size of the array command to set your needed parameters for your function calls so you can operate on your functions. And in many lines of code, the example in section 612 of your book shows that you can use the size of function to modify or create your arrays according to how big your data is. So that concludes what I'm going to talk about in chapter 16, except for this one additional video that I'm going to do talking about the privileges and it's kind of a scope, global versus local variables, and using static. And I'm just going to create a separate video to cover that rather than that one section that your book had on talking about declaring things static. So that's all for chapter 6 then. Bye now.